Okay. Uh-huh. Yeah. Okay, so the idea, what we're gonna talk about today is isomorphisms. Now, you might have seen this in linear, and let me just kind of give you an idea of what in the world you're actually doing in each of your courses, right? In every single course, you have some kind of object, right? Like in linear algebra, the object was a vector space, right? And let's say you're studying graph theory, then you have graphs. If you're studying modern algebra, yeah, modern algebra 1, this course, right? So this is kind of the first course in several courses. You have groups, right? In analysis, you'd be studying, well, metric spaces or versions of those. And topology, you're studying topological spaces and so on. Now in algebra, there are other things actually out there. There are rings and fields and all sorts of other stuff. Lots of other things. Same thing with analysis and topology. You could have additional requirements, like a metric space is actually just one where you have a notion of measuring distance between objects. So in Euclidean space, you have a nice distance function, right? How far apart 2 points are. But more generally, you have a metric, a measure of distance, but it satisfies some kind of axioms. So in every class, you study some object, right? And you get to the point where you have these definitions for what does it mean to actually be a vector space or a graph or a group and so on. And after a while, you start to study, well, what are some substructures that live within your structure? So far we've studied what are subgroups, right? Things that live within your group. And the next thing that we're trying to accomplish is what does it mean for two groups to be sort of equal? I should have gone back all the way to the basics. So in discrete, and even before that, what's sort of the first major object that you study are sets, right? So sets, okay? So what does it mean for sets to be equal, right? Well, you would actually have to compare the objects inside. So you have a notion of what it means for them to be exactly equal, but then you have a more general idea of what does it mean for them to be equivalent, right? Like you can build a more general notion there. So one idea that I'm kind of getting at there is with sets, what you could do is you could say, okay, how do you know, let's say, how do you know if you have the same number of objects in one set as another one? What you could do is you could build a bijection between them. And so like, for example, if you wanted to count the number of fingers that I have and compare it to the other hand, you could count them individually, or you can build a bijection. So it's much easier if you can build a bijection, because then you don't actually have to do the individual counts, right? You just know that you have a one-to-one and onto function, and you can verify that they are the same cardinality, right? So there's a general theme to each course, which is, what does it mean to fundamentally have these objects be equal to one another? And so in linear algebra, it's actually the first time you kind of see the real version of this, which is you have two vector spaces are isomorphic to each other. So they're not exactly going to be the same, but they share some fundamental properties with each other, okay? And without going into full detail, do you remember what vector spaces actually were abstracting? Vector spaces are where linear combinations make sense, okay? So in order for your vector spaces to be sort of equal or isomorphic, what you would want is you'd want there to be some sort of correspondence between how vectors behave in one space and another one, okay? So linear combinations in one have to make, there's a nice mapping to linear combinations in the other. But I think groups is going to make maybe there's fewer things to look at with groups. So maybe this definition will make a little bit more sense. So, okay, so let G and H be groups, okay? An isomorphism is going to be a function from G to H, okay? And it's an operation preserving bijection. So not only is it a bijection of those things being sets, right? Do you remember that groups are sets that happen to have an additional binary operation and they satisfy those four axioms, right? So what I actually want is a bijection. So I want it to be a one-to-one and onto function, which we'll use our previous knowledge to have or prove. And the last thing that I want is this. I want that if you give me any two objects in the group, and if I were to map their product, I would actually get the product of their mapping. So it's just one additional thing that you're going to end up having to prove. So if I gave you this function and I said, prove that it's a bijection and it satisfies this, you already have kind of 2/3 of the problem done in a sense. Okay. Now, what does this actually mean? All right. So I wanted to kind of dissect this a little bit. So it's easy to kind of gloss over the fact that this product AB is actually taking place in the group G, and this product over here, phi of A and phi of B, is actually taking place in H. So what you could do is, if you kind of carefully look at this, what you have is this equation is really phi of a product in the group G is going to map to a product in the group H. Now, they don't actually have to be products. It's just that a lot of times when we write things out, we write them as products, and then you can translate them using whatever the binary operation happens to be in your group. So more formally, I didn't want to make it look too crazy, but you could actually end up with this situation here. So you could have that G has some operation, which we'll call star. Hang on, let me see if I can focus this a little better. It didn't really change anything. Let's say G has this operation star, and H has this diamond operation, okay? So phi acting on whatever this operation is going to get mapped to, well, you have to figure out what phi of A is and phi of B is, and it's supposed to map to whatever their product would have been in H, okay? So I'm just making sure that you realize that this operation here is occurring in G, and this operation is occurring in H. Okay, we're going to do tons of examples, but I just wanted you to be aware of when you see this equation, it's kind of subtle, but something is happening here in G and something is happening in H here. Okay, another definition. So if the two groups happen to be equal, then the above definition, instead of calling it an isomorphism, you actually call it an automorphism. Okay, so there you're not actually necessarily trying to figure out if the groups are equal in a sense. You're actually studying whether or not you have a function that behaves really well. Right? More on that a little later. Sorry. Yeah, so it'll be about, yes, it's related to that, but with a permutation there, that's actually a function. A permutation is a bijection on a set to a set, but here you have a bijection, but these are also groups, so they individually have their own binary operation. So it's kind of like a yes and a no to your question. Okay, so I think a better version of the definition is this one here, because if you start to think of this definition in its individual pieces, then this will allow us to have a template of proving whether or not you have an isomorphism of groups. Okay, so G is isomorphic to H, and we'll write this notation here, just like you had in linear algebra for vector spaces, if there exists an isomorphism from G to H. Okay, so that is, you need these four things to happen. Okay, so the very first thing is there exists a function from G to H. So in other words, you want a well-defined function. Okay. Second thing, you want the function to be one-to-one and onto. So you remember that the definition for one-to-one, the version, at least for proving it, it would look like this. Right, and then definition of onto is this. So you already actually have, we've done examples where you you know how to do 1, 2, and 3, right? That already was on exam 1. So proving an isomorphism between G and H, the only additional thing is actually to prove this operation preserving step. Okay, so let me give you a visual. This right here is going to give us the template of proving. So anytime you have to prove G is isomorphic to H, you're going to do these 4 steps every single time. Right, so that's your template. But let's draw a picture because pictures are nice, right? So here's G and here's H. So H and G are both groups, okay? But what does this isomorphism mean? Well, individually, okay, within G, I have elements in this group, right? So I have an identity over here, and I have an identity over here. And let's say that I had A and I have B in this group, okay? Because this is a group, I should be able to combine elements using whatever the operation of the group is. So do we agree that there should be an element out there, which is the combination of these two, using whatever the group operation is, right? Now, so far so good, right? You can add more things in here if you want. I certainly will have to have an identity in this in here, but just for simplifying the picture of what this 4th property is doing, that's what we're drawing, okay? Just the 4th property. Now, I have a function from G to H, and it's a bijection. So I actually can map A somewhere, and that will get mapped to a point in H, and we'll call that phi of A. Okay. Similarly, B maps somewhere, and that'll map to phi of B. So far, so good? Now, what do I know about these 2 points? Well, they're in H because phi is a well-defined function. So everyone okay with that? So phi is a function that takes me from G to H. So I definitely know that these 2 points are in H. They may, can they be equal to each other? Well, the way that I've drawn it, I've sort of chosen distinct points over here. So they have to go to distinct points because it's a bijection. But if A and B happen to be exactly the same point, then they would be, right? But the way that I've drawn it, it should be like this. Okay, now these 2 points are in H, and H is a group. So do we agree that there should be a way to actually combine these 2 as well? So I should be able to take phi of A and combine it with phi of B using whatever the operation is. It may be addition, it may be multiplication. That's why I was kind of saying up here, you could denote it as this little diamond if you want, but we'll just say that it's multiplication for the sake of simplifying kind of what we're writing here. All right, so far, the only properties that I have used are 1, 2, and 3, and the fact that this is a group. Is everyone? These both are groups. So what does the 4th property say? The 4th property is actually ensuring that this element here maps to this element. It's actually saying that the function phi has to take me from here to here. So in other words, this product, whatever it happens to be, is actually equal to phi of A times B. Okay, that must map somewhere. Okay, it must map somewhere over here because A, B is in the group. So it must map to something in H, but it cannot map to something other than this. So that 4th property is actually ensuring this. Now, what is that doing intuitively? It's kind of saying that it's preserving the group operation. So how A and B combine over here is exactly how their image combines over here. So that's what we mean by an operation preserving function. In linear algebra, the definition was much more complicated. Not only did you have to have a bijection, you had to have that it satisfied 2 properties. It satisfied linearity and homogeneity. And how many of you remember what the heck that means? Yeah, it's t of x plus y is t of x plus t of y, right? And t of k times x is k times t of x, right? So those are, you're proving that it's a linear transformation plus a bijection, if you remember all those buzzwords, okay? But here, you're proving that it's a bijection, but it happens to satisfy this additional equation. So to be honest, all that practice that we did for proving one-to-one and onto functions, you only just have one additional step to prove that you have an isomorphism. Okay? Because groups have very few things going on. You just have one operation and 4 axioms. Okay, so if anyone has any questions so far, let me know.
For examples.
Yeah. Oh yeah, we're gonna do a ton of examples. Okay. Okay, very first example, hoping will help make sense of this. Okay, and we're gonna kind of follow the redefined version down below where we wrote it out in 4 individual kind of steps. Okay, so first example, here's my claim. So the claim is that Z4 is isomorphic to mu4. Okay. So recall Z4, what does that actually look like? So Z4 is 0, 1, 2, 3, and what's the operation? Yeah, this is addition modulo 4. Mu4, do you remember that this is the 4th roots of unity? So this will be +1 plus I minus 1 minus I. Okay. And what's the operation here? This is thought of as a subgroup of the complex numbers under multiplication, right? So this is just multiplication. Okay. So my claim is that these are isomorphic. They are fundamentally different as sets. Do we agree that they're not equal as sets, right?
Sure.
Yeah, they don't have the same elements. Okay, but as groups, we're going to prove that they are the same because they're isomorphic. So whenever you're talking about groups being the same, what we really mean is that they have an isomorphism from one to the other. So this is kind of interesting because I have a completely different operation over here, a completely different operation over here, but somehow fundamentally they're the same. All right, so let's figure out how to build a bijection. I'm going to have to spoil that for you because this is the first one you've ever seen. So let's define phi from Z4 to mu4 as follows, by the following. So phi of n, so n will be one of these elements in Z4. You're going to map that to I to the n. Okay. Now, first thing you have to figure out, is this well defined? Is this well defined? In other words, is this a function? Right? Whenever you hear someone say well-defined, they're talking about, is this a well-defined function? So all the inputs should get mapped to something, and everything in the domain needs to get mapped to something in the codomain, right? Exactly one thing. You can't have like one input go to 5 outputs, something like that. All right, well, let's figure it out. All we have to do is just figure out what phi of each of these elements are. Okay, what's phi of 0? Well, that's I to the 0, which is 1. So far, it's well defined, right? I have something in the domain getting mapped to something in the codomain, right? If I got like a 5 here, you could stop and say it's not well defined, so I don't even have to do the rest of the problem, right? Yeah. So far it is a function. I'm going from domain to codomain, but you got to show that for everything. Okay, so what's phi of 1? What's phi of 2? What's phi of 3? And as long as I'm getting something in the codomain each time, just one element, then I'll be okay. All right. So I to the 1 is I, and then I squared. Remember, I squared has that special definition that the square of that is -1. And I cubed, well, I squared is -1, so I cubed will be I times that, which is -I. Okay. So do you agree each time that this is an element of mu4? We good?
Yeah.
So yes. So phi is well defined. In fact, do you actually see, you also just showed by doing that work right there that it's actually also 1-to-1 and onto?
Yeah.
In fact, phi is 1-to-1 and onto. 1-to-1, because I have distinct elements getting mapped to distinct, distinct inputs get mapped to distinct outputs. Do you agree that everything in the input over here is distinct, right? And over here, there's no repeat, right? There's no two distinct inputs that got me a repeat. So that's the one-to-one. The onto, how do I get the onto? Well, that's the range. All the outputs, that's everything in mu4, right? There's nothing missing from mu4. Yeah. Exactly. So the first example that I'm giving you, the step for 2 and 3 is much shorter because there's no I mean, there is an algebraic definition, but there was only 4 inputs. So it was pretty quick. Okay. So we already proved steps 2 and 3. So that really just leaves step 4 here. So step 4, what are we going to do? Well, what I always recommend is when you're writing this step out, okay, you have to, this is why you have to be very, very careful. You have to pick 2 things in your group, G, the domain, and you want to write out what this equation is, because every single time this equation is going to depend on what your operations are. So you have to be very careful. All right? So let's call them N and M. N and M be in Z4, the domain. Okay. And what are we going to show? We are going to show that phi of something is phi of something, phi of something. Okay. Every single time you're pretty much showing this, but here's how you're going to fill in the blank. So I'm going to have N, and what's the operation in the domain? Yeah. So this is actually going to be an addition, right? You can add the mod 4 there if you want. That's fine. Okay. And what's the operation in the codomain? Yeah, remember the codomain is mu4, so the operation there is actually a multiplication. Okay. So every time you write out that equation, you can kind of just write it as if it's multiplication, but then you might need to shift these operations to specifically what they are. In general, I'd say 90% of the time, these are either going to be addition or multiplication, but you have to figure it out. So you're going to have kind of 4 possible equations that you're going to have to write, right? These could both be addition, addition, multiplication, multiplication, addition, or it could be multiplication, multiplication. Okay. Those are the most common.
Are we always going to have to just derive our own function?
That's a really good question. For exam 2, no, but beyond that, yes. In general, that's the hardest part actually, is building this. Okay.
Yeah.
Proving things. Yeah, that is the hardest step right there, is building that. The rest of this is sort of, you have kind of a procedure to follow. Okay. This is where the creativity is, kind of coming up with that thing. Any questions up to this point? So I just, all I did was I translated that step 4 to our context, okay? Because the domain happened to be, operation was addition, and the codomain, the operation was multiplication. So I highly suggest always writing out this show step. You'll get some partial credit for that. So I know what you're about to do. Okay? So now this gives us a starting place. So start with the left here. So phi of n plus m. And can I do anything with that? Well, sometimes you have to simplify the inside, but this will be an element of Z4, right? So my mapping knows what to do with it. It'll map it to I to whatever that input is, right? So this gets mapped to I to the n plus m, right? According to our function, this is the input, right? So it'll be I to whatever the input is. And now, do I have any rules of exponents that come to mind? Like, I'm trying to break this apart. So this is I to the n times I to the m. And that right there, this is phi of n, and this is phi of m, right? So this is phi of n times phi of m. So this is what we mean by operation preserving. So in other words, you sort of translated the addition problem to a multiplication problem. It's just in over here in Z4, that's what makes sense, is addition. And in mu4, That's okay. It doesn't, it gets carried along from here. So addition inherits the properties of addition from the general integers. You might need to involve the mod 4 if you maybe had to simplify this a little bit more or do something sophisticated, but here it wasn't necessary. Okay, so hence phi is operation preserving. Thus, by 1 through 4, we can definitely say that Z4 is isomorphic to mu4.
So there were things that are one not preserved.
Yes, yeah. You could have something that's a bijection but not operation preserving, and then it would not be an isomorphism. In fact, you could try to attempt to just build one by the same concept. You could try to build a bijection and map these things in such a way that it messes up this property here. Yeah. Well, it's harder to actually find this thing because you're sort of in a way trying to come up with a clever way to actually do that mapping. Now, let me give you another way to get some intuition behind what the isomorphism means. My claim is that what you're doing is all the data in this planet can be translated and understood in this world over here. Okay, so kind of think of it as like a translator. You're kind of doing math in one language, you could translate it into another language. Yeah, so it's like you're doing it in, I don't know, English, and you translate it to German. Although that's not a perfect analogy because not everything really translates really well, and it's not a perfect analogy, but it's pretty close. And so one way that you can kind of describe that, see what the dictionaries would do. Let's look at their Cayley tables. Okay, so let's look at the Cayley tables. Okay, so one can see finite groups are isomorphic by their Cayley tables, but things can get tricky by permutations. But things can get tricky if you had to permute rows or columns and things like that. Okay, so let me show you what I mean by this. So the first group was Z4, right? So we have addition modulo 4. So what's the Cayley table for Z4? I think that might have even been an exam question. Yeah, 0, 1, 2, 3. Okay, so you're doing addition modulo 4. So 0, this is the identity, so I'm just going to repeat what's above, right? Add 1 to all these, 2, 3. 1 plus 3 is 4, but modulo 4 is 0, right? And then 2, 3, 4 modulo 4 is 0. 5 modulo 4 is 1, right? And then 3, 4 modulo 4 is 0. And then 5 is 1, and 6 is 2. So there's our Cayley table. Okay, now what do I mean by, okay, things can get tricky with permutations. If I just draw the Cayley table for mu4 over here haphazardly, I'm not going to actually see exactly how things get translated. So what you're going to actually do is you are going to draw the Cayley table over here, but you're going to choose the ordering specifically based on the what phi is doing. So you know how we calculated what phi of 0 does, and phi of 1, and phi of 2, and phi of 3? This is how you're going to order things. Okay, so we're going to use 1, I, minus 1, and minus I. Okay, that's specifically the ordering because that matches what phi did up above. So you see, this is phi of 0, this is phi of 1, this is phi of 2, this is phi of 3. And the reason we care about that is we chose the ordering 0, 1, 2, 3. So we want to preserve that ordering here. Okay? So I have 1i minus 1 minus I. And over here, it's just multiplication. So all I got to do is just fill this up. And so 1 times anything, it's going to give me back what I have, because this is the identity, right? Which is good, because the first row was the identity for Z4. I times this is I squared is -1, negative I, and then negative I squared is negative -1, which is +1. Okay? -1, negative I, +1, and then that'll be I, right? Negative I squared is negative -1, which is +1. Negative I is I, and then negative I is plus I squared, which is -1. Okay, now if you translate this, okay, so do you see I'm really just translating back and forth using a dictionary, which is what phi is. Phi is like your dictionary. See that? So you translate via phi, right? It's exactly right here. In other words, do you see that what you're doing is 0 over in this world translates to 1 over in this world. 1 translates to I over in this world. 2 translates to -1. And 3 translates to -I. Do you kind of see that? Look at these two tables. For example, 2 plus 2 over here was 0, the identity, right? And 2 is this -1. Do you see -1 times -1 is 1, and that's the identity in this group. So do you see that's how it's preserving the group operation. So if I took 2 elements here and I did the group operation, I got the identity, I should get the same thing over here. Let's try another one. 3 and 2 give us 1, right? So that's -I and -1 give us I, and that's exactly the translation back to 1. So do you see? In other words, this you could take this whole square here, and if you use this translator and translate it, you'll get exactly what we have filled in over here. I don't know if that's better or worse, but that's kind of the idea. Is phi is telling you exactly how to translate everything that works in Z4 to how things work in mu4. And because it's a bijection, there's an inverse, so you can go either direction. Okay. Yeah. Okay. So when you say groups are equal, keep in mind that they do not have to have the same elements, right? Or the same operation. They fundamentally just have to be able to, you have to have a, when I say they don't have the same elements, you have to have this, if it's finite, they have to have the same number for sure, but because you need a bijection. But the important thing is that you're preserving the operation of the group, and that's the hard thing to actually do.
Oh, yeah, so I guess we have 2 groups of different number of elements, automatically say no, it's not.
Yeah, they can't be. Yeah, so in fact, it's much easier to prove 2 things are not isomorphic than to prove that they are, because it's much easier to just to find something that one group has that the other one doesn't have, and just say, oh, they don't share this property, so they can't be isomorphic. So after we do a few more of these, that's exactly where we're headed. We're saying, oh, it's so much easier to show 2 things are not isomorphic, because all you got to do is just find one thing that one group has that the other one doesn't. All right. Any everyone online? Nobody's saying anything, so I'm assuming that means hopefully that makes some sense here. Okay, so next example, this one's going to look a little strange at first, and then when you realize when you're talking about groups, it's not terrible. Okay, so here's a claim. So the claim is the real numbers under addition is going to be isomorphic to the real numbers, positive real numbers, right, under multiplication. So this right here is positive real numbers. Okay. Now, as sets, that's absurd, right? They're not exactly going to be the same set. Not every real number is a positive real number, but as groups, this is okay.
I guess so we're gonna say they're both uncountable.
Yeah.
Okay, so in terms of their cardinality, yes, they would have the same cardinality, right?
Yeah, it just
So the
was weird. It feels like two different cardinalities just because you're putting in positive.
yeah, reals are a little weird, right? That happens.
Yeah.
Or even an interval from 0 to 1 has the same cardinality as the whole real line, right?
I remember reading once there's the same amount of even numbers as even and odd because they're both uncountable.
Well, yeah, they're both, well, those are both countable, right? But
Or even, even that would be, they both be.
yeah. Well, what's weird is if you took the real numbers, you took out all the rationals, you get the irrationals, right? That's the same cardinality as the entire real line. But it seems counterintuitive because you removed elements from it, right? So how should they have the same cardinality? Well, this is because you kind of have to abstract the notion of same size, right? So you're coming up with a bijection. That's kind of going back to it makes intuitive sense when you're talking about countable things, but when it comes to uncountable, it's very bizarre. Yeah. Okay, so I'm going to have to give you the mapping. I'm going to have to spoil this again, right? So consider the mapping. Phi, and this is going to go from real numbers under addition to real numbers, positive real numbers under multiplication, and it's actually a pretty nice function. So phi of x, you're going to map your real number here to e to the x. Pretty simple function, actually. Okay, now, first thing you have to check, there's 4 things. If I'm claiming that this is an isomorphism, and that's my mapping, just going back to that first page, we still have to prove these 4 things. Okay, so you have to prove it's well-defined, one-to-one, onto, and it's operation preserving. Okay, so first thing, is this thing well-defined? So first, this mapping is well-defined since for all x in the real numbers, e to the x we know is positive, right? E to the x is always positive, and e to the x is definitely always a positive real number. Okay. So in other words, everything in the domain gets mapped to exactly one element of the codomain. Okay. Not answering whether or not it's one-to-one or onto yet. That's what we have to do next. Okay, so second, to show, right, so second, let's show phi is one-to-one or injective, right? That's the same name. Now, in order to do that, what are we going to do? Well, let x and y be 2 elements of the domain. Okay, and what are you going to do? Do you remember what you get to suppose? Sorry. Yeah, so the going back to our template of showing something as one-to-one, you're going to suppose now that phi of x is equal to phi of y, and then you will show that x is equal to y. Okay. Well, phi of x is equal to phi of y is saying e to the x is equal to e to the y. Okay. And as soon as you have exponents like this with the same base, they're the same base, they have to have the same, they have to be, the exponents will have to be equal. Yeah. If you want to involve calculus here, you could act natural logable on both sides, and that would give you x equals y. But I wanted to avoid having to do that. So B is one-to-one. You can actually prove 2 and 3 using techniques from calculus, but I'm trying to use the templates that we have. Okay, so the next one. So phi is show phi is onto. Okay, so the template of proving that is you pick something in the codomain and you show that there's always something in the domain that'll map to your chosen element of the codomain. Okay, so maybe going back to the template, I usually use the letter B. You can use the letter Y, it doesn't really matter. Let B be an element of the codomain. Okay, so an arbitrary element of the codomain. So remind yourself of that. That's the codomain. Okay. And when you show the one-to-one part, you start off by picking two elements of the domain. Might be helpful to remind yourself of that. Okay. So whenever you're doing the one-to-one, start out by picking two elements of the domain, onto pick something in the codomain, and then now show there exists something in the domain such that phi of A is equal to the B that you chose here. Okay. So this is the domain. All right. Well, can you cleverly think of such a thing? Now, if you can't, you can always do scrap work. All right. So here's how this would go. You would say consider A equals something. And now phi of A is phi of fill in the blank. And where does fill in the blank get mapped to according to our function? Yeah, E, yeah, we get mapped to E to whatever that blank is, right? So it would be E to something. And what do you want this to be equal to? You want this to actually end up being equal to the original thing that you chose, right? The B here. Yeah, natural log of what? If this was natural log of B, yeah, that's it. Okay. Now, if you don't see that, how do you get that? Well, you go over here into scrap paper land, right? And the reason I'm saying that this is scrap paper land is because generally you're going to break the rule of math, which is assume what you're proving, right? So over here, you want, what do you want? You want this equation to hold, right? So over here in scrap paper land, you could just illegally say, oh, well, let's just allow that. And what is phi of A? That would be E to the A, right? And if you wanted to, you're trying to figure out what A is, right? So what is A? Take natural log of both sides now. And now A is ln of B. See that? And now you just say, look, I'm a genius without showing me the scrap paper. And then you just say, that's ln of B, right? And now you just figure out what the rest is. So if I put ln of B here, ln of B here, E to ln of B, they cancel because those are inverse functions. So I get B. So does everyone agree that why this is scrap paper? Because you're kind of engineering what this actually has to be. Well, you can't assume it because that's what you want, right? You want to be able to always find an A. The one thing you probably should mention, though, is that ln of B is definitely in the domain. Do we all agree that ln of some real positive number is always a real number? This is definitely in R. The reason is because B was positive, right? Natural logs, the domain of the natural log function, you have to input a positive real number. You can extend the natural log over complex numbers, but even there you can't plug in 0. Yeah, you can plug in negatives though, but and in fact complex things, but it gets bizarre. Yeah, but over as a real function, the domain of the natural log is you got to give me a positive real number to plug in, and then the output is any real. So far, so good. I don't know if that is helpful, but at least you're seeing how I was telling you to kind of solve it on scrap paper and then just say, oh, look, I cleverly chose this. You know, if you read enough math books, you'll ask yourself, how in the world did they come up with this step? Because they just came up with it out of nowhere without showing you the scrap paper, right? They're like cleverly say, I chose this, and now everything works. I'm sure you've seen that.
Is there a way to do that for P? Instead of just being like, oh, this is the one. There's no clever work backwards method.
I mean, there might be more. There might be other ones that work. It might not be the only one.
Using intuition based on
Kind of, yeah. You'll see even in the general case when I have you kind of do them, coming up with that phi is never easy, actually. You know, it's like differential equations. Did you take that course? Yeah, you know, did you take that course? You know how you're trying to find a solution to this differential equation?
Oh,
And
yeah,
if you were super clever,
if you this was yeah, I remember that now.
well, if you're super clever, you could just say, oh, this is the solution, and I can verify it by just plugging it into the differential equation.
Yeah.
And to be honest, that's actually how some research in DiffEq works. People just have so much intuition behind how these types of functions work that they can guess a solution, and they don't actually have to derive the method in which they found it. You just need a solution to the differential equation.
It works, it works.
Yeah, so it's kind of funny that just having enough intuition, in other words, you're able to do that scrap paper thing without it just works out. We still have the new step, right? Everything up above we've already done, but the new step, let's translate that. So looking at, let's just look at this again. So back here, you got to pick two things in your group. And then this is the part that's going to be translated a little bit different each time. Now, you can use A and B if you want. I'm going to use X and Y just to remind ourselves that these are real numbers. But let X and Y be here. So this is the domain again. Okay. And you are going to show phi of X, Y equals phi of X, phi of Y. Now notice I'm going to always leave some space here and fill those in with the correct operations. So if you just write exactly what 4 says, you would write this. But in this problem, one of them is an addition, one of them is a multiplication, right? So which one is the addition? The addition is the domain, right? Because this one is addition, this one's multiplication. So I'm actually going to have to put plus here because that's the operation of the domain, and it's multiplication for the codomain. So it actually kind of matches our first example. Yeah. But just keep in mind, you kind of have, well, for 90% of the problems, 2 different possibilities here, either plus or multiplication, and this one's usually plus or multiplication. But it could be something like function composition or some other weirdly defined binary operation. So it's not always going to be like that. All right, so if I'm proving this equation, just start with one side, try to get to the other side. So start with the left-hand side. I have phi of X plus Y, and that's going to get mapped somewhere. Phi sends, what's phi defined as? Phi sends the input to up here, right? So e to the x. So this will become e to the x plus y. Yeah, it's exactly. This becomes e to the x, e to the y. And look, that's multiplication, right? And that right there is phi of x, and this is phi of y. So you have now verified this equation is true, right? Phi of x plus y is equal to phi of x plus phi of y. If you ever get stuck and you can't do this last step, what you could do is you could just start to simplify them separately. You would say this is equal to this, and then you could stare at these two and go, oh yeah, those are true because of some rule that I know, right? So don't just give up if you simplify it and you don't know maybe how to do this step. Start with the other side separately and see if you can kind of figure out how they would connect to each other, because that step is technically non-trivial if you don't remember some properties of exponents. Okay, so thus reals under addition is actually isomorphic to positive reals under multiplication. And this does have an inverse, right? Once you have a bijection, the inverse should also give you an isomorphism, actually. That's going to be a property. What would the inverse function be? Be natural log, right?
Yeah.
So natural log actually gives you a way to go from multiplication to an addition problem. That one is actually kind of interesting if you think about it, because in general, multiplication can be kind of a complicated thing, right? Before you had calculators, right? Multiplying large numbers or even fractions and things can be more time consuming than adding, right? That's actually how slide rules used to work. Have you guys ever seen those before? Slide rules? So the predecessor to the predecessor to a calculator. You had these two rules that moved.
Oh, abacus?
No, I'll show you someday, maybe. Maybe I'll show you.
I've never heard of that.
Yeah.
That's crazy.
If you had to do complex calculations really quickly under multiplication, there's this tool that they used to have called a slide rule. And what it would effectively do is it kind of had recorded on it a logarithmic table that would, but it was much faster for you to do an addition problem. So you would just quickly do the addition problem. You'd use this slide rule and it would calculate the multiplication problem for you. You could do other operations as well, but that was fundamentally one of the most useful ones, because if you had to multiply some things real fast, that was a way of doing it. But no need to do that anymore because you could just use a calculator, but there's some interesting history behind that. Okay, now example 3. What time is it? Okay, good. We got time. Okay, now let G be any group. And let phi from G to G be the identity map. Okay. i.e. Phi of x is just equal to x for all x in the group, right? So kind of a not very interesting function. It's well defined, it's one-to-one, it's onto, and it actually is operation preserving, but it is pretty boring. So this is an automorphism. This phi is an automorphism, but it's kind of a trivial one. This is called the trivial automorphism. Okay. Now, automorphisms are isomorphisms from a group to itself. So they're not trying to achieve whether or not the groups are equal in the sense that they're the same group. You're trying to actually answer some other questions about the group. Maybe the existence of some types of automorphisms could reveal some interesting properties of the groups. For example, if you had, I'll show you in a second, if you have this type of automorphism, the group might actually be abelian. So yeah, maybe there is an automorphism out there that if your group is an automorphism under this mapping, then it's cyclic or something like that. So that's kind of the idea behind automorphisms. They're supposed to reveal some properties of the groups. Okay. So let me give you an example of a non-trivial automorphism. So example, hopefully everyone wrote all that. Pretty much just said the identity function is a trivial and pointless automorphism. Okay. So now consider the group, the integer is under addition. I could actually just write Z because it's only that thing is only a group really under addition, right? Whenever we wrote that, we meant that was under addition, because under multiplication, it's not a group, right? It doesn't always have inverses, like 2 does not have an inverse in the integers. So let's define B from Z to Z as phi of n. I'm actually going to send it to negative n. So the negative of n. So what you're actually doing there is you're sending it to the additive inverse of n, because the additive inverse of n is negative n, because if you add the two, you get 0, right, which is the identity. But let's see, is phi an automorphism? Well, if you want to check something as an automorphism, you still have to check all 4 of those properties. So first, well, it's well defined. If n is in Z, do you agree that phi of n, which is equal to negative n, is in the codomain, which is also Z, right? So no problem there. Okay. Second, phi is 1 to 1. So the proof of that, let n and m be integers, and suppose phi of n is equal to phi of m, then negative n is equal to negative m, and therefore n is equal to m. Agree with that? I guess I should have said show n is equal to m, so you know where you're going, but that's the quick template showing that it's 1 to 1. On to I don't know, do you want me to use B and A? Okay, so let B be in the codomain. So just to be clear, I guess here, note this is the domain. So it's just confusing because these happen to have the same codomain and domain, but just to follow the template, be aware that when you start the 1 to 1, it's in the domain. You pick the 2 things in the domain. For the onto, you pick something in the codomain, right? Codomain. And now you're trying to show there exists something out there that gets mapped to this. Well, maybe you could just think of what it is. Consider A equals blank, right? So you're still going to show, I guess I could write that out. There exists something in the domain such that phi of A is equal to B. Okay. Yeah. So consider, fill in the blank, phi of A is equal to what? That's going to get sent. So you're going to fill in the blank, right? And this will get sent to negative fill in the blank. And what do you want this to be equal to? You want it to be equal to B, right? So you want phi of A to be equal to B. So if you want negative of something to be B, what needs to be in the blank here? Yeah, negative B, right? The only thing that'll get you B here, if you're going to negate it, is to take negative B, right? So I need negative B here and negative B here. And is negative B in the domain? Well, if B was an integer, if I negate it, it's certainly an integer. We okay with that? If you do scrap paper land, you get the same answer, right? So you want this. You want that, right? So in other words, you want negative A to be equal to B. So A is equal to negative B. It's probably easier to just do everything in scrap paper land than to kind of reverse this, but sometimes it's somewhat fast. I don't know. Use whatever method is fastest for you. That makes the most sense. All right, last step. Phi is operation preserving. So now let A and B be in the domain. All right, so now this is domain. And what do you want to show? Show phi of A plus B is equal to phi of A plus phi of B. You agree that the operation is addition in Z and in Z. This is the domain, this is the codomain. Okay. So be aware that what you write here is dependent on the situation. All right, so now just figure out what phi of A plus B is. Well, where would this input get mapped to? It's negative, right? It's negative. which is negative a plus minus b, or you could say it is negative a plus negative b. So that looks like you're using some kind of distributive property, which is essentially the case, but you could actually derive that from the very fact that the way this has to be. Okay, and this is phi of a plus b of b. Okay, so you're done. The reason I want you to see this is it is a non-trivial automorphism. So it satisfies the definition of an automorphism, but it's definitely non-trivial. So you can send an integer to its negative and get an automorphism. So that is a bijection. You can kind of think of it as you have the integer line, and you're sort of reflecting it upon itself, right? And not only does that give you a bijection, it actually is operation preserving. Okay. Now this is kind of interesting because, well, in general, are there other non-trivial automorphisms? And if you look at what that example is actually telling you, the more general version would look a little bit different. If this was a group and this was the same group G, what did we send n to? Yeah, so what is its negative as an integer? What are you actually doing there? You're actually sending it to its inverse. You see that? The inverse under the operation. So this example kind of leads us to an interesting question. So this brings up, it brings up an interesting question. Okay, so when is phi that goes from G to G defined by phi of G equals G inverse an automorphism? Okay, so example 4 shows it is for G being Z, right? Example 4 that we just did, that was the automorphism, right? You sent n to its negative. The inverse happened to be negative because that group was a group under addition. But what about in general? In general? That's actually a homework question. So the homework problem, I'll just spoil it for you. There's a special property that Z has, which is that it's actually abelian. Okay, so the homework question is this: show phi is an automorphism. It's not for this week, just so you know. This would be for next week. Phi is an automorphism if and only if G is abelian. Okay, so that's why this is kind of interesting. It's saying you have this, you have a classification theorem. Okay, the existence of an automorphism reveals something interesting about the group. So hopefully doing that homework problem shows you the usefulness of an automorphism, because on the surface it seems really useless, doesn't it? If the goal of isomorphisms is to show that the two groups are the same, automorphisms seem very useless in that pursuit because you already know that G is the same group as itself, right? There's no point in showing that. But an automorphism such as this one actually could reveal some interesting information about the group. See that? So this is an if and only if, so it's two parts. If it's a group, this will be an automorphism. And if this is an automorphism, then you'll get that this is a group. Okay. So try it out. My hint to you is that socks and shoes will be involved in that proof. Yeah. Okay. Now doing these examples, I'm hoping that you kind of see how if you have an isomorphism between two groups, so this should say let phi be an isomorphism, so not a new word. There's actually a space between the word and isomorphism there. So space those out. An isomorphism, I don't know what that would be, but an isomorphism is a thing. Okay, so let this be an isomorphism of two groups. Then you get a whole list of free properties. Okay, first one is that the inverse happens to also be an isomorphism. So that could actually be kind of interesting to you, like the one I was just mentioning before. Like e to the x has an inverse ln, and that actually gives you an isomorphism. Second property is very useful. That one is saying if you have, keep in mind, this is saying you have an isomorphism, okay? It's not if you have one of these properties, then you have an isomorphism. This is only one way, okay? So if you have an isomorphism, it forces them to have the same cardinality, okay? The converse is not true, though. If I have two groups that are of order 8, they do not have to be isomorphic because they both have 8 elements in them. But what you could do is you could use that fact to prove two things are not isomorphic because they had a different number of elements in them. So I'm trying to give you like a list of things to look for between two groups, because in general, it's easier to show two groups are not isomorphic by showing some essential properties of each group are different, right? Like maybe they have different size, or maybe one is abelian and the other one isn't, okay? So isomorphisms preserve commutativity. They have to both be abelian. It preserves cyclicity, so they both have to be cyclic. It preserves subgroups of specific orders, and even more. There's many, many more things that are preserved. Like, for example, if I have a group with an element of order 2, an isomorphic group certainly also has to have an element of order 2 in it. Okay? It preserves everything. There's nothing that one group should have that the other one doesn't, except for maybe what you call the objects and the actual operation itself. So, okay. And some more general things too. Like if you have a subgroup over here, you can push it forward using phi and build a subgroup of H. And if you have a subgroup of H, you can pull that back and get a subgroup of G. If you push forward the center of G and just translate what those elements are, you should get the center of H. Okay. So you get a whole laundry list of things that isomorphic groups have to share, which also gives you a laundry list of potential things that they might not share, and that could be useful. So let me just show you a really quick example. Is Z4 isomorphic to Z6? Okay. If you wanted to prove they were isomorphic using our standard technique, it could take you a long time because you got to try to build a function, right? But the quick answer is no, because, well, anyone? Yeah, the cardinalities are different, right? Z4 has 4 things in it, and Z6 has 6 things in it, and these are not the same, right? Isomorphic groups must have the same number of elements.
Makes sense because they wouldn't be one-to-one.
Exactly, yeah, yeah. Yo. Okay. You know what? Maybe I'll just give you one more and leave you on a cliffhanger, okay? Because I think our brains are a little bit fried. So is S3 isomorphic to Z6? Now, the order of S3 would be 3 factorial, which is 6 actually. So these do have the same number of elements, right? So the order of S3 is 3 factorial, which is 3 times 2 times 1, which is 6. And Z6 is equal to 6. So these are the same. So not enough to say yet. Okay, so that's always the first thing you should check if they have a different number of elements, because then you would immediately be done. Okay. What's something else I could check that's on this list?
What is the S3 group again?
The permutations, right? On 3 elements. Yeah. It would look, if you actually wanted to write it out, it would look like this, right? So S3, you'd have the identity, you'd have yeah, those are the 6 elements, the permutations, right? Do you remember?
Yeah.
Yeah. I'm not adding in all the 1 cycles that are there, but those are the 6 elements. Their permutation, remember these are bijections from a set of 3 objects to a set of 3 objects. So each one of these represents a actual little function, right? Like this represents the function from 1, 2, 3 to 1, 2, 3 that goes like this. 1 goes to 2, 2 goes to 1, and 3 goes to 3. So you get, there's 6 different functions there, and the operation is group composition.
Yeah.
Right.
Well, we know those aren't abelian.
Yes. Yeah. You proved that in homework, right? That was a homework question. So S3 is non-abelian, and C6 is abelian. So that is a property that one has that the other one doesn't have, which therefore they cannot be isomorphic. So thus, S3, oh, I'm sorry. Yeah, S3 is, sorry. I thought I made a claim that they were. It was a question. So S3 is not isomorphic to Z6. You could write it like that they're not isomorphic.
You started doing that.
So in other words, the answer is no, right? All right. Oh, okay, cool. All right. I think that's a good spot to leave off on. I'll start with this example. So if you want to try it yourself, is U8 isomorphic to U10? So you could think about that if you want. Okay. But we will pick up there on Wednesday. All right. Cool. Have a good night. Hopefully it's somewhat nice.
Tomorrow,
Yeah, I think tomorrow it's supposed to be. Well, who knows though.